Okay, let's talk about electric fields. So, maybe it's a lavender. Well, it's an exciting new color that we haven't used before. And let's all just try to enjoy it. Okay, so just a quick recall. If we have a positive charge, we draw field lines coming out of the positive charge. And the reason why is because we base field lines on what a positive test charge would experience if it were put near here. Anywhere around an object that's positively charged, you would have a repulsion. Okay? The opposite is obviously true of a negative charge. A positive test charge would always be attracted from any angle towards the center of this area of negative charge. Okay? With that in mind, you can sort of figure out now what would happen if you had, say, this scenario. Okay, positive test charge would be held that way. Here, you can figure that you'd have a repulsive vector pushing away from the positive, and you'd have an attractive vector pulling towards. The sum of those two vectors is directly to the right. As you get closer, the intensity of the field increases, and that's related to a square from the distance away. So in other words, force is proportional to the inverse square of distance away. So in other words, the closer you get, the stronger the field gets, but it's not linear, it's exponential. And anyway, what that serves to do is set up field lines that look like this. Okay, this is a classic kind of electromagnetic scenario when you have opposite charges nearby one another. Okay, and if you have two like charges, slightly different. So if you put your positive test charge right in the middle, it would be equally repulsed from either, and it would essentially have a zero net force. So the way we represent that is this. One thing I like to think of that helps me sort of understand what's going on with fields is I sort of like to imagine them like wind. Okay, so imagine that there's wind blowing out of positive charges, right? And if two winds blow into each other, well, they're going to have to go somewhere. Okay, so a little like that. And you can imagine that the positive test charge is like a little ping pong ball or something like that that's being blown by the wind, right? So you can imagine what would happen if we released this or allowed it to flow. It would sort of follow the field lines out, just like a kite in the wind. And if we this, now the wind blows into these areas of charge, right? So you get this kind of same scenario going. Winds are equally pulling the charge in either direction, and again, right, it's equally attracted now, and so there's no net force in the middle. So there's kind of your general outline of electric fields. Okay. We also learned that there's a law called Coulomb's law that dictates the amount of force between two charged objects. Okay. We don't use negatives or positives in the sense that we would in like a normal vector problem. Okay, we have to, as physicists, understand that in the case where we have two like charges, the force is repulsive, and where we have unlike charges, the force is attractive. Okay, that's up to us to realize and figure out, which way objects have the overall net force acting on them. Okay. Okay, so for the second part here, let's talk about the electric field itself. Okay, so measuring the electric field. So when we were doing Coulomb's law, we compared it to Newton's law of universal gravitation, right? And we find that the formula is essentially identical. So in gravity, we have this concept of, that's a different straight line. this concept of little g, right? The acceleration due to gravity near the surface of an object, or also known as gravitational field strength, right? And we measure it in newtons per coulomb. How many newtons of force? Newtons per coulomb. My goodness. Newtons per kilogram. There we go. I'm already jumping the gun. Newtons per kilogram. So in gravity, right, the field strength of a gravitational field is measured in how many newtons every kilogram field. On Earth, it's 9.81. This also, you might remember, converts into an acceleration, so meters per second squared. So you often see g just written in terms of an acceleration, but really what it is, it's how many newtons of force are acting on a kilogram near the surface of an object, or actually really anywhere that a gravitational field exists. So we want to know what the analog to that is in electricity. How do we measure the strength of an electric field? Well, the symbol, first of all, is curly E. Okay, so this is the symbol for electric field. You know, it's the analog to G. G was measured in newtons per coulomb, and newtons per kilogram, and E is measured in newtons per coulomb. Okay, so in other words, the electric force for a given amount of charge. So what does that mean? What that means is, if I have an amount of charge gathered here, and I measure some space outside of this, say over here, okay, let's say I put a 0.5 coulomb batch of charge here, and I experience, 10,000 newtons of force. Okay, so the electric force here is 10 times 10 to the 3 newtons. Okay, so how would we go about sorting out what the electric field strength is? I think you can see it's pretty simple. Okay, 20,000 newtons per coulomb, or 2 times 10 to the 4 newtons per coulomb, of course, here. So that is our field strength at this point. Okay, what happens to the field strength as we move closer? It increases. It increases not linearly, correct. It increases at a square to distance. So if I go half the distance away that I am now, what would your expectation be to happen here? What would happen, do you think? If I went to half the distance away that I am now, what would this increase by, do you think? A factor of 4, correct. So it's like taking this down here and squaring it to get a quarter on the bottom. This increases by a factor of 4. Right? If you double the distance away, you'd expect it to drop by a quarter, and so on. If you put it 3 times closer, it should go up by a factor of 9, and so on. Does that make sense? Okay, sweet. So there's the general idea of what's going on with electric field strength. When we were doing current electricity, which I find odd that we do it in this order, but it's kind of the way it's written out. What if I were to move this here, and I had to push it in? Well, in that scenario, then what we have is we have some force applied over a distance, and we actually have to do work to make that happen, right? So this is where the concept of electric potential energy comes from. When we're talking about moving charge in a field, work is required to do that. Now, when I push it in here, force does not stay constant, right? Force is going to increase at a square to how far away I am. But we could potentially, right, figure out what the difference is between these two areas of potential. Then what we could do is we could say that the delta V, right, the voltage between here, we could sort out what that would be, okay? So when I push it in here, I've added electric potential to it, and that means as it is repelled back out, we can tap that to do work for us, okay? So this is just a backwards tie-in to electrical current, right? And if we let this happen in a wire, we're sort of more or less, doing current electricity. If we have a steady supply of charge, we can feed positive charge in here and have this field push it out and do the work for us. We can tap that, right, to do work for us. Now, there is another way to define or talk about fields, and that is combining two formulas into one. So let's derive, right? We've got this Fe up here, right? So we've got Fe, this is the force acting on our charged object of charge Q. And if we roll back up, what we'll see is that Coulomb's law also has Fe in it. So what we can do is we can substitute KQQ over R squared into here, right? So we can do this. K Q Q over R squared over Q, which translates to these two things crossing off of each other, and you get K Q over R squared. Okay, so this formula, what it's for, what it will tell you. You guys okay with the math there? Okay, just double checking. Just want to make sure you understand why I'm allowed to do this, right? We're dividing it and then dividing it again. So this is like the numerator, and essentially we have two denominators if you want. Another way of writing this would just be to put your Q beside here. Algebra, eh? It's, yeah, it can be tricky. Just work it out in your mind, right? If you're ever, just a little side note, a little side hint. If you're ever not sure you're doing your algebra right, like, try it out. Like, just use simple numbers. K is 2, Q is 4, R is 2, and Q is 2. Oh, maybe these aren't good numbers, actually. So 8 over 4 over 2. 8 divided by 4 is 2, divided by 2 equals 1. Or 8 divided by 2 up here, right, is 4 divided by 4 equals 1. Okay, so it works, right? So if you're ever stuck on algebra, just put it in simple numbers and give it a try. That's my pro tip of the day. Okay. Others are just cool with algebra and they won't have to do that, but every once in a while it's good practice. Okay, so what does this mean? What can we use it for? So we have this new formula that looks like this. And essentially what this formula is good for is if I have a known amount of charge collected in some place, I don't know, like 1 times 10 to the negative 6 coulombs, okay, and I go 1 centimeter away from that collected charge, I can figure out what the field strength is at that point. Okay, so let's do it. What is the field strength 1 centimeter away from a 1 microcoulomb charge? And we can say it's positive if you want. So the field will point out. So we know it's a positive test charge. How do we get something to be positively charged, by the way? How does that happen? What's one way we can do it? How do we get a positively charged object sitting in space? How can we do that? Sure, okay, well the only way actually is really to remove electrons somehow. What are some ways to get electrons off an object and have it statically charged? That's one way to do it that's common. Yeah. Okay, so sure, friction is one way. If we rub it with another insulator. Are there any other ways? Do you remember? Think back to grade 9. No, superheating is not what I'm thinking of. We could take another charged object and touch it to that object, right? As long as they're both insulated from the ground, they will take on the amount of charge in the other object. So like, let's say we have sphere 1 and sphere 2, and this has a 10 coulomb charge, this is a 0 coulomb charge. We can touch these together, and when they're touching, the whole thing gets a 10 coulomb charge, and when we take them apart again, right, and that charge will distribute evenly, assuming this is a conductor, right? That charge will be distributed evenly, and we'll end up with 2 5 coulomb charges, right? Does that make sense? So we can charge by friction, conduction, and there's one other way. We can also charge by induction. With induction, what we would do is we'd have this neutral sphere, we'd have this charged sphere, say 5 coulombs, and we bring it nearby. Let's say this is positive. What that will do is it will attract towards the one side all of the negative charge, and you'll get a separation of charge within this sphere, assuming it's a conductor, right? And then what you can do is you can just simply touch a ground to the other side, and so what will happen is all the negative will move to the right, leaving a positive on the left. And then electrons will be attracted up from the ground, and what you'll actually get is you get this thing overall with a negative charge because you've added extra electrons. They're essentially being attracted through space via the field, right? There's a field here, and pulling electrons up into this object, negatively charging it. So a positive object can charge another object without touching it in the opposite way, as long as there's a ground attached to the other object. Okay, so that's called induction. Induction. So conduction, induction, and friction. There's a similar concept, right, with the way things heat, right? You can heat by friction, if you want to think about it that way. You can conduct heat into an object, and you can have induction or inductive heating going on. I guess maybe heating, like infrared heating, for instance, or heating through UV. What do we call that? Forget. Radiation, right? It's like radiation, I suppose, in a way. Anyway, I'm getting off topic. So the point is, what is the field strength at some distance from a known amount of charge? And like gravity, we consider all that charge to be concentrated at the center of the object. Okay. So let's say it's 1 centimeter from the center of this object. So E in this place is K. What's K? Well, it's 9 times 10 to the 9. And what units is it in? Should be newtons, right? Well, why don't you know what we'll do as a little exercise? We'll figure it at the end what the units have to be. Okay. So you've got charge, in this case, 1 times 10 to the negative 6 coulombs. And you've got, this is in terms of centimeters, so a centimeter is 1 times 10 to the negative 2 meters. Everything's got to be in meters, kilograms, or seconds, MKS, right? And then square that. So we've got meters squared on the bottom. We've got coulomb on top. And we need our electric field strength to be in newtons per coulomb, right? So it's got to be coulombs negative 2, and it's got to be meters squared, right? So the meters will cancel off, and one of the coulombs will cancel off, and we'll get an answer in newtons per coulomb. Does that make sense? Good, so we've got that sorted out. 9 times 10 to the 9 times 1 times 10 to the negative 6. Up here you should end up with a value of 9 times 10 to the 3, right? And then you're dividing it by 1 times 10 to the, what happens here? 1 times 10 to the negative 4, right? So you should end up with 9 times 10 to the negative 1, no. 7, right? Should end up with 9 times 10 to the 7. Can someone just double check that, please, and make sure that that's correct? Fact checkers. Okay, so there we go. That's how you figure out field strength near a charged object. Okay. Now, what does that mean? It means that if I were to place a 1 coulomb charge here, okay, if I were to place a 1 coulomb charge here, it would experience 9 times 10 to the 7 newtons of force repelling it. Remember that a coulomb is an absolutely massive amount of charge, so you get these astronomically high forces. We never really deal in full coulombs of charge unless you're like a lightning storm or something like that. So yeah, so there you go. There's your field strength. Field strengths tend to seem really, really large, but because we deal with such small fractions of coulombs, we get reasonable, forces out of even really large field strengths. Okay. So one last thing, we've sort of talked about what happens to fields near circular objects or amounts of charge kind of just sitting there in space. In electricity, though, a lot of times we end up dealing with parallel plate systems, and you'll remember from current electricity, there's some symbols that we're used to seeing, like, for instance, the symbol for a cell. Okay. So why does a cell symbol look like that? So we've got a gap here, and we would say something like there is a 2-volt potential across here. Okay. And if we hook it up in such a way, we can actually get charge reacting to this voltage, to this potential, and moving through here, okay? So what does this represent? Well, this represents, in a way, it represents a parallel plate system with opposite charges on it, okay? So let's just talk about that for a minute and see what that would look like. So what if we have two parallel plates, okay, so they're metallic plates sitting here, and we give one a bunch of extra positive charge and one a bunch of negative charge. What do you think the field is going to be like in between here, using what you know? How do we test a field again? We use a what test charge? Okay, so imagine no matter where I place a positive test charge within here, assuming this line's perfectly straight, it should be, what type of force would the positive test charge always experience, no matter where I put it in here? Exactly. So within a parallel plate, field lines are parallel, okay? Field lines are parallel within a parallel plate system, okay? So what we're going to do going forward, but not in this lesson, what we're going to do going forward is we're going to look at what is the relationship between the distance here, how far apart the plates are, the voltage or potential, and the force on charged objects within here. And we'll do things like talk about, you know, what happens if I put an electron here and release it? What happens if I put a proton here and release it? What happens if I put an alpha particle here and release it? And so on. Okay? Essentially, you can make like a particle accelerator if you want. If you complete these in a circuit, right? Now what's going to happen is you're going to have charge flowing around, right? It's going to start to flow around if you complete the circuit. And it will, you know, I guess a battery is sort of like this, but it also supplies not just the field, but a supply of charge to flow through the circuit. And boom, away you go. You've got now a battery powering a circuit. If you just have a parallel plate within a system like this, and you actually apply this, what have I created here? What do you call something like this? Does anyone know? Yeah, it's a capacitor. That's right. So you have buildup of charge over here, and you get a corresponding negative buildup of charge over here, and you have this gap that lives in between here, and you can, as you want, you know, you can, depending on the size of these plates, you can store significant amounts of charge on them, and then release it or tap it when you want, like a little mini extra battery, I suppose, within the circuit. Okay, so enough for today.